Hello, this is Mr. Boyce, and this is video number two, getting ready for our final exam. This is probably the longest individual unit. This is stoichiometry. It's been a while since we've done it, and there's a lot going on with it, but a lot of things that we learned in this unit we continue to use. So hopefully this won't seem too foreign to you. Uh, all right, well, let's just go ahead and get started. This is First off, stoichiometry. Let's think about this as your stoichiometry island chart. This is the kind of thing you're going to want to write down on your note card that you get to use on the test if you finish a review. And that is, you can start at volume, mass, or molecules. All right. And then from there, um, you can go from your mole to mole back to volume, mass, or molecules. Well, that's a lot neater looking that way. Uh, some things to keep in mind. Volume, you don't really have a choice here. Volume must be in liters. So if you have it in something like milliliters, or something like you're going to want it to convert that. So as long as it's in liters, you're good. Mass is going to need to be in grams. So things like milligrams, kilograms, those are very common. If you get those, convert them before using this chart. And then molecules, this is Avogadro's famous number 6.02 times 10 to the 23rd power. This is how many things are in a mole. Now from here, you have mole of A, and on this side you have mole of B. So here, this is a very, very, very important step. When you're here, what you're doing is mole to mole of A to mole of B, and you do this with the balanced equation. Okay. So basically, you've got step 1, 2, and 3 here. Let's see here. All right, first one. For the reaction of carbon plus hydrogen, and remember hydrogen is diatomic, so that's H2, reacts to form CH4, how many holes, whoops, typo, how many moles of hydrogen are required to produce 0.6 moles of methane? So no, moles of hydrogen refers to H2 and not H because it is diatomic, it's not paired to anything else, so therefore H2. And this question is asking how many moles of hydrogen. So my B is moles of hydrogen. And my known quantity, that's always going to be my A. And in that case, it's going to be moles of methane or CH4. So this is my A and my B. So here, let's take a look. I don't need to worry about volume, mass, or molecules. I'm starting in moles of A, and I want to work my way to moles of B. So this is a very simple one-step question. So as always, start with your given measured quantity. And in this case, my given measured quantity is 0.6 moles of CH4. So 0.6 moles of CH4 or methane. Okay, now this is all about converting, and converting, don't forget, I don't have to put a lot of thought into what I bring down. I bring my unit, moles of CH4. That's what comes down here. Okay, and again, I'm going from moles of A to moles of B. So since I'm already in moles, I can go to moles of H2. And this is what the whole point of a balanced equation is the mole-mole ratio. So here we go. For every 1 mole of CH4, I need to react 2 moles of H2. It's a little hard to read. Okay, so H2, I'm going to put a 2 in front of that, and CH4, I'm going to put a 1 in front of that. And that's pretty much it. Uh, your answer is going to be 0.6 times 2, which is going to be between 1 and 2. So remember, whenever possible, I'm going to give you answers in a range. Your responsibility is to do the actual problem and put the correct answer round to 2 decimal places. Uh, Okay, next, I want first to identify what do I want? What do I know? What do I want to know? So I want grams of magnesium nitrate. So this is my B. This is what I want. And this is my A because this is my given measured quantity. So I know I have 8 moles of water. So let's start with that. 8 moles of H2O. And I know I'm going to convert it. So I'm just going to move moles of H2O to the bottom. So think of this as your starting block in a race. Even if you're not sure what to do, you can always write down your given measured quantity and bring your unit down. You can always do that. And from there, sometimes it'll make more sense what to do. Now, I'm in moles of A. So my next step, my only option, is moles of B. Now, what I want is grams of B. So I'm going to go from moles of B to mass or grams of B. So I've got 2 steps I need to do. So moles of A or H2O, 2 moles of B, which is magnesium nitrate. So Mg and O3, 2. Okay, and I'm going to fill in the numbers when I know I'm good to go. Now I want grams, so I'm going to move my unit down. Moles of Mg and O3, 2. And if you just want to rewrite these A and B because it's easier, you can do it. Just make sure you keep them straight. And from there, I can go to grams of magnesium nitrate. Okay, now I know this is good. Notice I don't really care about the 8 because no matter what number I put there for this particular reaction, uh, moles of H2O, for every 2 moles of H2O, I react with 1. If there's no number there, it's 1, obviously. 1 mole of the magnesium nitrate or B. And for 1 mole of B, I'm going to add together 1 magnesium, 2 nitrogens, and 3 times 2, 6 oxygens. If I add all of that together, I get my molar mass. That's 148.3 grams. Okay, let's shorten this up a little bit so I have some room. All right, so in my calculator, I'm going to put 8, highlighter, 8 divided by 2 or times 1/2, same thing, times 148.3. That's 8 divided by 2 times 148.3. If I put that into my calculator, my answer is going to be between 580 to 600 grams. It's going to be up to you to find the specific correct answer, but it should be within that range. If it is, you know you got it right. Okay, number 3. Again, A and B, all right? So I've got 4.3 moles of KBr. I'm just going to move my 4.3 here. All right, here's my A, and I want grams of potassium chloride. Here's my B, okay? And I'm going to go from moles to grams once again. So same two-stepper right here. So let's start with what we know. Let's start with 4.3 moles of KBr, and then convert, bring my unit down as always to moles of my B, which is potassium chloride, which is right here, which is KCl. I can always fill in the numbers later. For now, I want to know what my game plan is. And I know I'm always going to take my unit and bring it down. So moles of KCl, whatever goes up must come down. And what I want is grams. So grams of KCl, and I'm good to go. So first off, KBr, the balance equation for every 2 moles of KBr, I am going to create 2 moles of KCl. So mathematically, this doesn't make much difference in the calculator, but it really makes a pretty big difference for me to do it this way because I brought down KBr and I put KCl on top. And then when I bring KCl down, then grams goes on top. And that's important for my math. Like I really need to know that. And so if I add a potassium and a chlorine, that comes out to about 74.55 grams for every 1 mole. In my calculator, I know 4.3 times 2 over 2 is just 4.3, but you can just put it all in the calculator if you want. But 4 times 3 times 74.55 is going to equal somewhere between 315 and 325 grams of KCl. So make sure you're within that range and you're good to go. Okay, for a reaction, and notice this one's even balanced too. How nice is that? How many grams of zinc oxide? So this is what I want to know is grams of zinc oxide. I found my B. Can be produced from 7.3 moles of oxygen. Now, oxygen, of course, is O2 because this isn't connected to anything. And so this is my A. First thing I'm going to do, as always, is start with my given measured quantity, and that's 7.3. And we're going to do a lot of these, and we're doing a lot of these on purpose so that there's a bit of repetition and you get good at this. Hopefully you did all of this worksheet before watching me do it. So 7.3 moles of oxygen, which is, of course, O2. All right, so again, I'm starting right there in moles of A. So my only other option is moles of B. And then from moles of B, I can go to liter, mass, or molecules. And while we're up here, let me just point something out. At STP, standard temperature and pressure, 1 mole of any gas will occupy 22.4 liters. That'll become important later, but just FYI. Okay, so moles of oxygen to moles of B, which is zinc oxide. That's here. This is my compound. So I have it in moles, but I don't want it in moles. I want it in grams. So let's bring that bad boy down to grams of zinc oxide. Now I can start filling in numbers. And for oxygen right there, I've got a 1, and ZNO, I have a 2. So for every 1 mole of oxygen I react, I can produce 2 moles of zinc oxide, which makes sense because there's only 1 oxygen in zinc oxide. Okay, and 1 mole of zinc oxide, if I add that up in my trusty calculator, it tells me that 81.4 grams is equal to 1 mole. So in my calculator, I'm going to put 7.3 times 2 times 81.4. Notice I always know if I need to do multiplication or division because I'm writing this out in dimensional analysis. It makes it much easier for me. So if you put that into a calculator, your answer is going to be within a range of 1,150 to 1,200 grams of zinc oxide. All right, let's just keep chugging along. So number 5, this one here, how many moles of water? Here's my B, and my given measured quantity is moles of hydrogen. That's my A. Now in this case, this is super easy. If I look at my chart, I'm in moles of A and I'm just going to moles of B. So great. But I do need to balance it. So if it's not balanced, you got to do that. So let's balance this thing. Two hydrogens, cool. I've got two oxygens here, but only one there. So I'm going to need to put a 2 here. Doing that meant I now have 4 hydrogens. So I've got to go back over here and give myself 4 hydrogens. So basically 4 hydrogens and 2 oxygens can make 2 waters. So that's the ratio it has to happen in, or I can't do this equation. So let's start with my given measured quantity, my starting block, my 5.55. And again, this number doesn't really matter to me until it's time to do math, because no matter what number is there, this conversion would work for this formula. So moles of hydrogen, which is H2. So moles of hydrogen to, I want moles of water. Okay. And when I balance my equation, I see 2 moles of H2 will react to form 2 moles of H2O. So this is basically 5.5 times 1. Like I would give you a range, but at this point, that's there's not really much point. So 5.5 times 1 is going to equal 5.55 moles of H2O. So this is a 1-to-1 ratio. And there you go. Hey, how many grams of sodium chloride are produced with 1.33 moles when 1.33 moles of chlorine reacts with excess sodium? So when you see excess sodium, that means you just don't have to worry about the sodium. You have as much sodium as you need to do to react all of what you have. Okay. So grams of sodium chloride, that's what my question is asking for, 1.33 moles of chlorine. That's what I know. So I've identified my B, I've identified my A. So let's start with A, sounds like a good place. 1.33 moles of chlorine. Now chlorine is diatomic, so that's Cl2. Okay, don't have to give this any thought. My unit, whatever is on top, goes down. So moles of Cl2. And I'm going to go into my mole to mole ratio. And so sodium chloride is NaCl. So I have it in moles of sodium chloride, but I don't want it in moles. I want it in grams. So one more mole NaCl, 2 grams of NaCl. So now I have my game plan put together, but I don't have all the information I need. I need to balance this. So I'm gonna put a 2 here, and that's 2 sodium, so 2. So just like the last one is a 2-1-2 balance. And so Cl2 right here as a 1, and that has 2 for NaCl. So let's put us a 2, if I can get it to cooperate. 2 NaCls, and 1 mole of NaCl. If I add up a sodium and a chlorine, that comes up to 58.44 grams per mole. And so 1.33 times 2 times 58.44 is going to equal something in between 150 to 160 grams of NaCl, and you'll be able to figure that out with your calculator. The important part is how to do it, and we are moving right along. How many grams of carbon dioxide are produced when 60.03 grams of propane burn completely? At this point, I'm hoping you're like, oh my God, again, like I know how to do this. That would be awesome because then you're going to do really great on the test. So let's just keep this up. 60.3 grams of protein, and I want grams of carbon dioxide. I have identified my B. I have identified my A. I'm halfway there. So let's just go ahead and start. 60.03 grams of propane. This is propane. This is C3H8. C3H8. Don't have any choice here. Just move that unit down. Grams of C3H8 to moles of C3H8. Okay, and my B is in grams, so I'm going to have to do some change. Mole of C3H8 to grams. Oh, I did something wrong here. Definitely did. Okay, let's look at what I did. So I'm starting in grams and I'm going to grams. And so I tried to jump forward. All right. I skipped a step. So I'm going from grams of A to moles of A, moles of A to moles of B, and then moles of B to grams of B. So this is 3-step, and I tried to do it in 2, which is not going to work. Okay, so grams per mole, moles of A to moles of B, which is carbon dioxide, so CO2. And now I can do this. So remember, when I'm looking at these, the only way I can compare two different things is the mole-to-mole ratio. They weigh different amounts, they have different attributes. The mole-to-mole ratio is how I can relate one to the other. And if I skip it, it's not going to work. Okay, so from here, I'm going to look up all of my numbers that I figured out earlier. And 1 mole of C3H8 is equal to 44.1 grams. And then, I don't have a balanced equation, so I don't even know what to put in this mole-to-mole ratio thing. So let's figure it out. 3 carbons to 1, so let's put a 3 there. 8 hydrogens, water's only got 2, so 4 times 2 is 8. Good job. Uh, oxygen, I've got 3 times 2, so 6 in the CO2, plus another 4 in the oxygen, that's 10. So let's put a 5 on the O2 for 10 oxygens. That means I have one of these. So now I can do a mole-to-mole ratio, which is great. So C3H8 is a 1 to CO2 is a 3. So a 1 to 3 ratio. Next, I want moles of CO2. 1 mole of CO2 is equal to 44 grams. Okay. And notice something, if you're paying attention to the math, you might notice that, oh, the molar mass of the propane and the molar mass of the CO2 are pretty close to each other. So they're practically going to balance each other out. And so when I do my math, if those balance each other out, then I kind of expect 60 times 3. My answer should be somewhere around there. And if it's not, then I should really go back and double check my math. So, but in the calculator, just to get the correct 2 decimal places, I'm going to do 60.3 divided by 44.1 times 3 times 44. And when I do that, my answer is going to be with about 180 grams, but make sure that you go back and find the actual specific answer to get your proper credit. Okay, number 8. How many grams of hydrogen are required to produce 15 grams of ammonia? Well, if you're not sure what ammonia is, you are sure what hydrogen and nitrogen are, so it kind of narrows it down. So my A is going to be my given measure quantity, 15 grams of ammonia and grams of hydrogen. So I'm going all the way from grams to gram. That's going to be 3 steps. So let's start with what I know. 15 grams of ammonia or NH3. And I know I'm going to bring my unit down, grams of NH3 to moles of NH3. Okay. Now it's time to relate one to the other. So let's move moles of NH3 down and go to moles of B, which is hydrogen or H2. And this is gram to gram. So let's move moles of H2 and convert that to grams of H2. All right, now I already know for the mole to mole ratio, I'm going to need to balance this equation. And so I'm going to do that real quick. And that's going to be 3, 1, and 2. So if you take a look here, actually, maybe that's a little quick. Let's just go ahead and do this. All right, so I have 2 hydrogens here and I have 1 hydrogen here. So I can put a 2 there. I'm sorry. Oops. I have 3 hydrogens and 2 hydrogens. In order to balance that, I need the lowest common denominator. 3 times 2 is 6. So let's set it to 6 hydrogens by putting a 2 here and a 3 here. So I have 6 hydrogens on both sides. Nitrogen and 2, and hey, nice. I've already got 2. So that's good the way it is. So 3 times 2 is 6. 3 times 2 is 6. 2 and 2. So 3, 1, and 2. This is my coefficients. This is my mole to mole ratio. So awesome. Okay, so 1 mole of NH3, if I look that up, 1 nitrogen plus 3 hydrogens is going to come out to 17 grams. And NH3, I've got a 2 there, so let's put a 2. And H2, I have a 3. All right. And then 1 mole of H2 is going to weigh right about 2 grams. So I'm ready to do the math. So in my calculator, this one I'm going to do a little bit different than the previous ones. What I'm going to do in a older calculator, one that doesn't have a fractions function, what you can do is, in this case, 15 divided by 17 times, so you're going to do multiplied by parentheses 3 over 2. So you're going to multiply it by 3 over 2, or 3 divided by 2, and then close your parentheses and times 2. So again, 15 divided by 17 times parentheses 3 divided by 2, close parentheses, times 2. And if you go through all of that, your answer is going to be somewhere in between 2.5 to 3 grams of H2. All right, we're getting pretty close. Let's keep going. How many grams of silver are produced when 65 grams of copper is added to silver nitrate? So first off, do I need to do this? Like, is copper strong enough to break up silver? Let's find out. Okay, that's fine. Here's silver. Oops. And is copper strong enough to break up silver? And I don't even need to find copper on here, but let's see. There it is right there. So copper is higher. Silver is pretty low on that chart. So most of the time silver, yes, you can. So this will happen. and it'll happen in the reactions there. Why don't we just go ahead and balance it while we're already talking about it? Copper, I have one on both sides. Silver, I have one on both sides, so that's good. Nitrate, NO3, I have two over here, so that just had to throw a wrinkle in it. So let's put a two there. Now that gives me two silvers, so let's go ahead and put two silvers on both sides. And I've got one copper, two silvers, two nitrates, and a balanced equation. So cool. How many grams of silver from 65 grams of copper? So I have identified my A and my B. Let's start with my A, which is 65 grams of copper. And let's move my unit down like always. Okay, I'm going from gram to gram, so I'm going to go the whole stretch. So grams to moles of copper, moles of copper to moles of my B, which is silver. And then always bring my unit down to grams of Ag or silver. All right, and then for this one here, not much math, just look at the periodic table, and 63.55 grams of copper is equal to 1 mole. So copper in my balanced equation is got a 1, and silver has a 2, so very important step. That's the only way you can relate these things. And 1 mole of silver, according to my periodic table, weighs 107.87 grams. Hopefully at this point you're getting really fast at this stuff. So 65 divided by 63.55 in my calculator, it's going to know that means I have about 1 mole of copper. You know, it's going to be a lot more specific. This is a 1-to-2 ratio, so therefore I'm going to produce about 2 moles of silver, and each one of those moles weighs 107.87 grams. So therefore 65, oops, 65 divided by 63.55 times 2 times 107.87, and it's going to come out to 218 to 222 grams of silver, somewhere within that range. I have faith in you. You'll be able to figure it out. Okay. Whew. We're on to something kind of new. Not really, but kind of. All right. So I don't really like the way this formatted, so I'm going to just change plus. I'm going to put that down there just so I can see it. Let's go ahead and balance this. This is 2 aluminum, so I'm going to put a 2 here. Oxygen, I got 2 on one side, 3 on the other. I can't make that unless I do a lowest common denominator. So a 2 here and a 3 here for 6 oxygens. Now that did throw off my aluminum, which I previously thought I knew, but now I have 4 aluminums. But just because I wrote a 2 doesn't mean I have to keep it. So I'm going to put a 4 here, and 4, 3, and 2 is my balanced equation. Okay, now limiting versus excess. This is going to be a little bit different. So if you've kind of been spaced out because all the questions were the same, now we're going to do something a little different. So first off, I need to know which one can make more, which one can make less. If I run out of one ingredient of aluminum oxide, I can't keep making it. So if I run out of aluminum or if I run out of oxygen, I'm done. I've got limited and excess reactants. So to figure out the limiting and the excess, notice I've got 3 of each. So not really much of an A and B on this one. I got 2 A's and 1 B now. And so I'm going to look at both of them. 3 moles of aluminum and 3 moles of oxygen. Okay, and I want Al2O3. This is my B, right? And so I'm just going to write B just to make it a little easier. So this is where the balance equation comes in. And for here, I've got, very important, I put this in correctly, 4 moles of aluminum for 2 moles of my B or my aluminum oxide. So I'm going to put a 2 here, and I'm going to put a 4 here. And 2 over 4 is the same as 1/2. You can use your calculator if you want, but half of 3 is equal to 1.5. I think most of us can do that. Here, moles of O2, I've got 3 moles of O2, so I'm going to put a 3 here, and moles of B stays the same as 2/3, and 2/3 of 3 times 2 is 6, divided by 3, so 2, which makes sense, 2 moles. Okay, so what that means is, with my 3 moles of aluminum, I can make up to 1.5 moles of aluminum oxide. Once I've done that, I'm out of aluminum. So it really doesn't matter how much oxygen I have. I can't make aluminum oxide without aluminum. And so the most I can make with these two amounts is 1.5 moles of aluminum oxide. Now, pay close attention. This is actually asking how many grams. So I know the most I can make is 1.5 moles. And I also know that 1 mole of aluminum oxide, if I add up 2 aluminums and 3 oxygens, is going to be equal to 1 mole of aluminum oxide, Al2O3. Okay. And then to get my final answer, what I'm going to do is the number of moles times the molar mass. So 1.5 times 101.96 grams is going to be equal to my answer, the number of grams that I can make. And that is going to be between 150 to 155 grams, which makes sense. If 1 mole weighs just slightly over 100, then 1.5 moles should weigh somewhere in the 150-ish range. So there you go. Mm. All right, formatting is a little off here. Sorry about that. But number 11, and you can barely see the question, but 1 mole of gas at STP, what does that equal? That is going to equal 22.4 liters. So 1 mole of any gas at STP is equal to 22.4 liters. Make sure that you know that. Aluminum reacts with hydrochloric acid. How many grams of aluminum are necessary to produce 11 liters of hydrogen gas at STP? So let's find what are A's and B's. So this is asking things a little bit different, but not that different. 11 liters of hydrogen gas at STP. Uh, and so that's my A. And what I want is grams of aluminum. Okay. And so that's my B. And notice we've already got the balanced equation here for us. So that's awesome. This is going to be slightly different than the last one. So let's start with 11 liters of hydrogen gas, which is, of course, H2. I'm going to bring my unit down, which is liters of H2 to moles of H2. Okay, now I want grams of aluminum, so I've got a few steps to do. Moles of H2 to moles of aluminum, and then moles of aluminum to grams of aluminum. So let's go ahead and fill all of this in. So this is the important thing to remember. Let's write this in red. 1 mole of H2 or any gas is going to occupy 22.4 liters. Now, my balance equation tells me that 3 moles of H2 is the product of reacting 2 moles of aluminum. And according to my periodic table, 1 mole of aluminum is 26.98 grams. And there we go. So this is a little easier than the molar mass. It's just 22.4. So in my calculator, I'm going to do 11 divided by 22.4 times 2 over 3 times 26.98. And if you put that in there, your answer is going to be between 8 to 9 grams of aluminum. Okay, trust me, we're getting pretty close. I know this is a long one. This is definitely the longest unit. This question is way easier than it looks. How many moles of carbon and hydrogen are required to produce 10 moles of methane or CH4? And this is just a mole to mole ratio thing, right? This is already balanced for me. So in other words, this is a 1 to 2 to 1 ratio. So if I have 10 moles of methane, then this is 1 to 1. So that's going to be 10 times 1. And this is a 2 to 1. So that's going to be 10 times 2, which equals 20. Okay. So how many moles do I need? Well, I need 10 moles of carbon and 20 moles of hydrogen because it's a 1 to 2 ratio with that. So pretty easy question. Okay, we have a balanced equation, which is nice. That's always easy to see. We have a given measured quantity, but we have another given measured quantity. What this is asking for is what the limiting reactant is. Now, if you pay attention to this, this can be way easier than it looks. You just really need to take it to moles to figure out which one makes more moles. So let's start with iron, 1.32 grams of iron, grams of iron to moles of iron, and then moles of iron to moles of iron oxide, because that's the only thing we're creating. So there you go. And I can just stop at moles. I don't really care how many grams or anything it makes. So according to my periodic table, oops, forgot. 1 mole of iron weighs 55.85 grams. So 55, whoops. And according to my balance equation, 2 moles of iron can produce 2 moles of iron oxide. So it's a 1 to 1 ratio. Uh, and so for that one, I'm going to put that in my calculator, and that's going to equal 0.0236 moles of iron oxide. Now let's shrink this up so I can have a bit of room here. Okay, next I want to compare that to my liters of O2. So let's start with my given measured quantity for that one, and that is 0.490 liters of O2. Move my unit down, liters of O2 to mole of O2. And then moles of O2 to moles of iron oxide. So 1 mole of O2 or any other gas at STP is equal to 22.4 liters. And or let's see, on a balanced equation, 1 mole of O2 is going to form 2 moles of FeO. So in my calculator, I'm going to do 0.490 divided by 22.4 times 2. And that is going to come out to 0.0438. And so let's compare the two. So the iron can make 0.0236 moles of iron oxide, and the oxygen can make 0.0438. So in other words, the iron is going to run out first. So that is my limiting reactant. Okay, in a Bunsen burner, methane reacts with oxygen to produce CO2 and water, shown in the unbalanced equation below. Um, so let's go ahead and balance it. One carbon, 4 hydrogens, 2. So let's put a 2 here. Oxygen, I've got 2, 4. So 2 in the CO2, 2 in the water. So let's put a 2 here. 2 times 2 is 4. And now I am balanced. What mass of water can be produced with 18 grams of methane and excess oxygen? So this is not really anything new. So let's just find our A and B. Mass of water, so obviously that means grams. It doesn't always say grams, but that's what that means. From 18 grams of methane, so I'm going gram to gram. 18 grams of methane, which is CH4. Move down our unit, grams of CH4 to moles of CH4. Okay, and then mole to mole ratio, so moles of H2O. And I want mass, so mole of H2O to gram of H2O. Okay, so let's see here. 1 carbon and 4 hydrogens is equal to 16 grams for 1 mole. According to my balanced equation, CH4 has a 1, so I'm going to put that there. Water has a 2, so I'm going to put that there. And 1 mole of water is equal to about 18 grams. So if I put that into my calculator, that, let's see, is going to be equal to somewhere between 40 and 41 grams. Now, of course, since this is a multiple choice, you can probably guess what the answer is for that one. In order for the reaction to succeed, for every 2 moles of methane, there must be at least how many moles of oxygen? You are going to see questions like this. So for every 2 moles of methane, there must be how many moles of oxygen? So this is a 1 to 2 ratio. So therefore, for every 2 moles of this, I'm going to need 4 moles of O2. So that's my answer. The coefficients in a balanced chemical equation represent the mass ratio. No, mass can be different. The mole ratio of the substances in the reaction. Yes, it does. Total number of electrons. Nope. Total number of elements in the reaction. No. So the coefficients is what you do when you balance, and that gives you your mole-to-mole ratio. Okay, percent yield. So we're out of stoichiometry. Let's see this real quick. So percent yield equals, this is actually in your formula sheet. actual yield divided by theoretical yield times 100. Okay, so this says that in the equation below, the theoretical yield is 58.34 and 44.34 is what you actually did. So 44.34 divided by 58.35 times 100 equals your answer. So you just want to put that in the calculator, or of course you can just convert 44.34 to 0.4434 and not divide by 100. Either way works. Okay, how many moles of H2O could be formed if 12 moles of H2 and 7 moles of O2 are allowed to react? So this one is actually pretty quick and easy. So 12 moles of H2, mole to mole ratio, H2 to moles of water. This is already balanced, so 2 moles of water for 2 moles, that's a 1-to-1 ratio. So 12, and then 7 moles of O2. Bring your unit down. So H2O is going to stay at 2, and O2 is a 1. So this is actually 2 over 1. So 7 times 2 equals 14. So I can't really make 14 because I'm going to run out of H2. So therefore 12 moles is the most I can make, and also my theoretical yield. Okay, mole ratio of NaOH to aluminum hydroxide. So I've got NaOH to aluminum hydroxide. According to my balanced equation, NaOH is going to be a 6, and aluminum hydroxide is going to be a 2, but none of these are 6 and 2, but I can reduce it to 3-to-1. So there's your answer. Whew, last question. Okay, this one is kind of important. We've seen a question like this before, and a lot of people got it wrong. I think they just maybe misread the question. So I want to identify the limiting reagent, the excess reagent, and the product. So I have one reagent and I have another reagent. They are going to combine to form the product right here. This is new. Now here, substance B, notice there is no substance B in the product side. So therefore I used up all of the substance B. So that is my limiting reagent. And then right here, notice I have excess. I have more left over in the products, which meant I had more of that than I could use. So that is my excess reactant. Wow. Okay. Promise that is definitely the longest unit. Thank you for sticking with me. Hopefully the repetition helps you to do really well on the test, and I will see you in gas laws.